Today, we're going to continue our integrating rational functions journey. Just to quickly recap, we're looking at we start with the numerator and the denominator and compare the degrees. If the degree of the numerator is greater than or equal to that of the denominator, then we use long division. If the denominator is quadratic with real zeros, or the degree is greater than 2, then we'll use partial fraction decomposition. So factor the denominator when you can over the real numbers. If the denominator is quadratic with complex zeros, we can leave that unfactored because we'd have to factor it over the complex numbers. We don't want to do that. But if the denominator is quadratic with complex zeros, then we'll get arctangents and natural logs in our integral. And if Q has an X term, then we're still going to get arctangents and natural logs, but we can complete the square to figure out what those how to break up those arctangents and natural logs. So in service of this idea, let's suppose that we have an integral. Let's say the denominator is going to be x squared plus 9, like I did yesterday. That's either going to be arctangent of x over 3 or 1/2 natural log of x squared plus 9. But in the numerator, I'm going to put in x plus 5. The strategy that we've seen in the past is to break apart the x over x squared and the 5 over x squared plus 9. So our strategy here is to break this into what we'll see as the natural logs and then the term for the arctangents. So one of our terms is going to be an x over x squared plus 9. And the other term will be a 5 over x squared plus 9. I don't know why I wrote completely new integrals, but that's the way it's going to go today. So this is how we're going to break things apart. The x over x squared plus 9, because the x is the derivative of the denominator. So here, we're just going to make the substitution w equals x squared plus 9. So that dw is 2x dx, and so a 1/2 dw is an x dx. So this first term is just getting the substitution treatment. The second term is the x squared is a constant over x squared plus 9. That's just going to produce arctangents. So when we integrate, the integral of x over x squared plus 9 is going to give us a 1/2 natural log of x squared plus 9. Since x squared plus 9 is always positive, I don't need to worry about the absolute values. Plus, then here we're going to have 5 times the integral of 1 over x squared plus 9. So I'm going to have 5/3 arctangent x over 3. And then plus c. So what we're using in the second term is we're just remembering that the integral of 1 over x squared plus a squared. So in this one, we just have to remember the integral of 1 over x squared plus a squared is 1 over a arctangent of x over a plus c. We can get there by doing trigonometric substitution, but we don't have to do trigonometric substitution. We can just remember this one. This is one of our core integrals to remember. Any questions?
Could you go over the ln portion? So it's just I'm having a hard time understanding where the ln came from.
In the x over x squared plus 9, we make the substitution w equals x squared plus 9. So we're integrating a 1 over w. So over here, the x dx is a 1/2 dw. So the integral becomes 1/2 the integral of 1 over w dw.
Got it. Thank you.
And so that's where the natural log comes up. All right, but like I said, we don't, when we integrate 1 over w, we get absolute value of w. But when we look at it as x squared plus 9, we say that's never negative, so I can drop the absolute values. All right, so I'm going to make an adjustment to this. Let's see, I still want the 9, so I'll go with a 4. Yeah, that'll work. So we're going to make an adjustment to this where I'm going to change the denominator to have an x term, x squared minus 4x plus 13. But I'm going to keep the numerator the same. What we're going to notice is that breaking it up with an x and then the 5 is not going to work in this case. That's not going to be what we want. So we look at our denominator. It's quadratic with complex zeros. We know that because if we complete the square, that's going to be x minus 2 squared, and then it's going to be a plus 4 and a plus 9. Plus 4 completes the square. That leaves behind a plus 9. And since the constant, this plus k, is positive and our parabola opens up, we're not going to have any real zeros. So I didn't figure that out by solving. I just have looked at many quadratics over the years, and completing the square is a better way to read polynomials than the quadratic formula. I know y'all love the quadratic formula, but I got to tell you, the quadratic formula is trash. It's just terrible, especially the way that we do it, because you miss out on all the cool stuff. So much better to look at this and say, and besides which, we have to complete the square here anyway. And it's such an easy square to complete. It'd be a real tragedy to be like all complete using the quadratic formula on something that I'm handing you with the leading coefficient of +1 and the coefficient of the x is even. I mean, come on. This is designed for completing the square. I'm avoiding the factoring out -1s. I'm avoiding the fractions. Everybody should like this, even though y'all shouldn't be afraid of fractions at this point in your mathematical career. But all that's beside the point. I'm just kidding around. You can use a quadratic formula. I won't say anything. I'll just silently be embarrassed for you. All right, what are we talking about? Oh, yes. So I noticed that the denominator is quadratic with complex zeros. So I'm going to complete the square, and x squared minus 4x. To complete this square, I'll need a +4, and I'm going to break that off to 13. So that's going to leave a +9. So this is going to be an x minus 2 squared plus 9. I'm going to break apart. I'm going to break this into two terms like I did before. I'm going to have a term for that's going to give me natural logs with a denominator, and the denominator is going to be an x minus 2 squared plus 9. I'm going to, just like before, I'm going to have a term that's going to deliver a natural logs, and then I'm going to have another term that still has this denominator, just like before. And this one's going to give me arctangents, just like before. So the term that I'm expecting to get arctangents from, that's going to have a constant in the numerator. The term that I'm going to get natural logs from is going to have a linear in the numerator. The important thing is that the numerator be a constant multiple of the derivative of the denominator. So we're not just going to be able to put an x over an x minus 2 squared plus 9. Because if I do the same thing, if I'm expecting natural logs to show up and I make the substitution, w equals x minus 2 squared plus 9, then dw is 2 times x minus 2 to the first dx. So the 1/2 dw is not x dx, it's x minus 2 dx. That tells me what I have to break apart into the natural log term. So in that term, I need to keep an x minus 2 in the numerator. To make this substitution work, the numerator has to be an x minus 2. The two numerators have to add up to an x plus 5. And so that tells me that my numerator over here has to be a plus 7. So because of the x term, that changes what the derivative of the inside is going to be in the substitution term. I want the numerator to be the derivative of the inside to make the substitution go. That's what made this go. W is x squared plus 9, dw is 2x to x, so a half to w is x dx. That's why I kept just an x up here. But down here, now that I've shifted things horizontally 2 units to the right, I've got to shift my numerator 2 units to the right as well. So I'm going to break apart the x plus 5 into an x minus 2 to be the derivative of the denominator. That's what happened here. This is where the question is. We reserve an x plus 2 to be the derivative of the denominator. We need x minus 2 to be the derivative of the denominator. And that comes from here. I know I'm going to get natural logs because I'm going to substitute w equals the denominator. To make w equals the denominator, I have to have a dw, that's the derivative of the denominator. That's how the natural log is going to work in this case. Now I can integrate this term to be a 1/2 natural log. I don't need absolute values of an x squared minus 4x plus 13. And then I have the 7 is going to be a plus 7 over my a squared is still 9, so 7/3 arctangent. And instead of x over 3, I have an extra x squared here. Instead of x over 3, I'll have an x minus 2 over 3. And then plus c. So that's what it all looks like shifted over because of the b term, or because of the value of b. Same problem, shifted 2 units to the right in the denominator. Any questions? The question that you're having right now is, how do I decide that it's an x minus 2? And we got to remember how this natural log, how the natural log term works. First of all, we've got to remember to know what we're going to get. We're kind of past the point where we can just kind of follow our nose through a problem. We kind of have to expect, we have to predict what's going to be happening. Quadratic with complex zeros means arctangents and natural logs. A constant over the quadratic is going to be the arctangent. Linear over quadratic is going to get natural logs. We know that if there's an x term, we're going to have to complete the square. And when we complete the square, we know that that's going to throw off what the numerator has to be. If there's no x term, then I can just keep the x over x squared and integrate that. And then constant over the x squared, x over x squared plus 9 to get the natural log, constant over x squared plus 9 to get the arctangent. But if things are shifted because I had to complete the square, then the derivative of the numerator, or sorry, the derivative of the denominator is going to be different. So I'm going to have to make sure that it matches what the derivative of the denominator needs to be. So make your substitution. That'll tell you what the numerator needs to be. And then the other numerator is just whatever subtract to get the other numerator. X plus 5 minus x minus 2 is going to give us the 7. Other thing to note is that if we make the substitution starting here, we come to the same conclusion. So if we start with w equals x squared minus 4x minus 13, then dw is 2x minus 4 dx. And so a half dw is still x minus 2 dx. Final note for as far as the style guide goes, if you leave the completed square version inside the natural log, that's totally acceptable. Just be careful with your parentheses. Any questions? How's everybody? Okay?
Yeah, just wrapping my head around where that 3 came from. I know it's from the 1 over a arctangent x over a. So
yeah, a squared is 9, so that's the 3. So if a squared is 9, then a is 3, so 1/3 x over 3.
Got it.
And the reason that this is an x minus 2 inside the arctangent is we're doing a substitution, because I want x squared plus a squared, but I've got x minus 2 all squared plus the a squared. So w equals x minus 2. dw is dx, and we can see that the x minus 2 is just going to show up where the x is.
Got it.
Any questions? It only seems like it's a lot to remember because it's a lot to remember. And you have to remember all of it, all the time, in perfect detail. So I don't know what y'all's complaining about. All right. Let's take a look at another problem. Let's remember the 3 things we start with. The first thing we check is the numerator. The degree of the numerator has to be less than the denominator for our integrations to go. So second, we check the denominator. Complex with real zeros, we're going to expect arctangents and natural logs. We might have to complete the square, so watch out if we need to complete the square. And then third, we decide if we are going to have to use partial fraction decomposition or not. So it's going to be some combination of these algebraic techniques to get us through integrating any rational function. All right. Let's take a look at the second example for today. Let's see, it's 8-2. You know things are getting serious when class consists of 2 examples. It's even more serious when class consists of 1 example. That seems crazy. And then it gets even worse when you find out sometimes there'll be 1 example and you're going to spend multiple classes on it. So let's take a look at 2x cubed. Already, you know, should be expecting what's coming up. Plus x squared plus 18x plus 12. And let's divide this by our favorites, x squared plus 9. We'll look at that denominator and say x squared plus 9 is quadratic with complex zeros. So I'm going to get natural logs and or arctangents. And then I'm going to be saying, that's great, but you skipped number 1. Number 1 is the numerator is of degree greater than the denominator, and that means division. Then you can notice that the denominator is quadratic with complex zeros, so we'll get natural logs and arctangents. If there's an x left over, natural logs. If it's a constant, then we'll get arctangents. But at least we don't have to complete the square. And we're not going to have to use partial fraction decomposition because the denominator is already sorted out. All right, so those are the things that we want to notice right away about this function. First, we're going to need long division. So the degree of P is 3, and the degree of Q is 2. So we need long division. We notice that Q is quadratic with complex zeros. So we're going to get arctangents and natural logs. Not necessarily and all the time. Arctangents or natural logs is what I should be saying. But I've been saying it ands for so long, I'm not going to be able to change now. But we also notice that the denominator is quadratic with complex zeros, and the degree is not 3 or more, so we won't need partial fraction decomposition. So the algebraic technique that we will need here is long division, because the degree of the numerator is greater than that of the denominator, so we need to divide. Division in polynomials works the same as division with numbers. We say x squared minus 9. I want to set it up in the traditional way. I'm not sure what your long division tradition looks like. I don't remember. I don't know how you were raised. So I'm not familiar with how you were raised, so I'm just going to use the traditional way. If you have more interesting ways to do long division of polynomials, then I'm all for checking that out. So the long division is going to go the same way as long division in numbers. If I wanted to divide, let's say, 3 into 17, the first question is always the same. How many times can I subtract 3 from 17 without going negative? So when I put the 5 up on top, that means I can subtract 3 from 17 5 times without going negative. The process itself, you don't have to actually get this correct. You just have to make sure that you multiply correct. But for polynomials, we're going to kind of have to get this one right the first time. So then we do the same thing here. How many times can I subtract x squared from 2x cubed? That means I'm going to have to have I can do that 2x times, because 2x times x squared is 2x cubed. We're asking the same question that we did with the numbers. How many times can we subtract x squared from 2x cubed without going negative? 2x times. We can subtract x squared from 2x cubed 2x times. The next thing that we do in the division is to actually do the subtraction. We can subtract 3 from 17 5 times before going negative. So let's subtract those 5 3s. 17 minus 5 is 2. The subtracting of the so sometimes in the algorithm we're just taught 5 times 3 is 15, then you subtract. You're just doing what you said you wanted to do in the first place. We can subtract 3 from 17 5 times, so let's subtract those 5 3s. That's what we're doing here. Let's subtract those 5 3s. And then there's 2 left over. We can no longer subtract 3. We can't subtract 3 from 2 without going negative, so we're done. That's what indicates that we're done. And that's why 2 is the remainder, because can't subtract 3 from 2 without going negative. So that's what tells us we're done. In the polynomial land, we can subtract x squared from 2x cubed 2x times, because 2x times x squared is 2x cubed. And when I subtract them, I'll end up with 0. But I'm not just subtracting x squared. 2x times 9 is a plus, 2x times 9 is 18x. I don't want to put that under x squared, because we only add things that are the same, and when we add them, it doesn't change what they are. So 2x times plus 9 is plus 18x. We can subtract we can subtract x squared from 2x cubed 2x times. So let's subtract them. 2x cubed minus 2x cubed is no x cubed. That's what we wanted to happen. X cubed minus no x's is x squared. 18x minus 18x is no x. And we still have this plus 12 to deal with. Because when we subtract x squared plus 9 2x times, we end up with x squared plus 12. That's what that line is. That is us taking this line, let's see. This line right here is taking the 2x cubed plus x squared plus 18x plus 12 and subtracting the 2x times x squared plus 9. And coming up with x squared plus 12. In the same way that this 2 was 17 minus 5 of the 3s. In the number example, I can no longer subtract 3 from the 2 without going negative. But in my polynomial example, I can subtract some more times. I can subtract an x squared from an x squared. And I think, how many times can I do this? I can do this 1 time. we can subtract x squared from x squared one time. Then I multiply. Let's do that. Let's take this x squared, and subtract it from x squared plus 12 one time. 1 times x squared is x squared. 1 times 9 is 9. I'll line them up under things that we can add. X squared minus x squared is nothing by design. If that doesn't happen, you've messed up. Go back and fix it. In numbers, it's easier to fix on the fly, but you got to go back in polynomials. 12 minus 9 is 3. So this line right here, this 3 comes from the fact that I took x squared minus 9, or x squared plus 9. Oh, it's x squared plus 12. We took x squared plus 12, and we wanted to subtract an x squared plus 9. And we can do that one time without going negative, which means we just have to exactly cancel out the x squared terms. It's okay if it's a negative 3. So we can now rewrite our rational function as a 2x plus 1 plus a 3 over x squared plus 9. So our original integral we're going to rewrite that as a 2x plus 1. That's going to be the whole number parts. Plus the remainder is 3. And we'll divide by the x squared plus 9. Now, the fraction part is a constant over a quadratic with complex zeros, and that's going to give us an arctangent. So now we can integrate the terms. The integral of 2x is x squared. The integral of 1 is x. The integral of 3 over x squared plus 9 is 3 over 3, which will simplify. Arctangent of x over 3 plus c. So for a final answer, we could say it's x squared plus x plus arctangent x over 3 plus c. If you're worried about how long that took, it only took a long time because I was explaining how long division works. Because one of my concerns is that we might have forgotten how long division works. Or if it, in the case of the thinking about it in terms of subtraction, we might not have known how to do it in the first place. Any questions? In a related note, in the polynomial example, we had to usually, I don't know what incantations you were taught when you were a kid and you learned long division, but I was taught bring down the next thing. So like bring down the next term, because I wasn't taught this properly. I was programmed with an algorithm that I've since had to think about to try to explain to people. I think that's the big challenge. With an algorithm, then they can't explain it to other people. They can't pass the knowledge on. They just like, oh, this is just what I do. And so when you're called upon to actually explain what's going on, you're ill-equipped to deal with it. So I had to kind of dissect what's going on in division. This goes back to my algebra class. I know none of you were in my algebra class, but I think of multiplication as repeated addition. That's the way I cast multiplication. And so that means division is going to be repeated subtraction. And I think repeated subtraction is a little bit better than just set 3 goes into 17 5 times. Here's the addendum. I know we're running overtime, but here's the addendum. Let's suppose instead of 3 into 17, I wanted to divide 3 into 170, 170, that's fine actually. The problem here is that the wording in the program, in your programming, may start out the same way. You go 3 goes into 17 5 times, which is, and the problem I hear is I see, where's the 17 in here? We leave out the part that that's not 17, that's 17 tens. So we're not subtracting 3 from 17 5 times. We're subtracting 3 from 70 50 times. We subtract 3 from 170 50 times. And so when we write 5 times 3 is 15, just under the 17, we're subtracting 150 because of the place value. And we don't have 2 left over, we have 20 left over. And then we're going to say subtract 3 from 20 6 times. And so that's why the next digit is going to be a 6. So it should look like 56. 6 times 3 is 18. So let's subtract 6 more 3s and end up with a 2 remainder. Now, what this has told us, a lot of times what I see people leave out in their thinking, this means that if we just looked at 3 and the 170 and said 3 goes into 170 56 times, that's what we're trying to figure out. We're just breaking it off into pieces. We're breaking it into place value. This is the value of place value. So people that are opposed to teaching things like place value because they didn't learn that, it's like, well, the people that are complaining may not have learned that, but I friggin' guarantee they were taught that and they just don't remember. I promise you that that's what's happening. And it may be that they weren't explicitly taught this thing, but the explanation that they're trying to say is the better way, the old way, the way that I remember it. That way is using that knowledge. They just don't see it that way because they're not professionals. I'm not blaming them for that. I'm not blaming anybody for not knowing how to do some math stuff or not understanding what the math stuff is. But as soon as you start complaining about things, now we have an issue. And if you can't explain to your kid how to do their homework, then just get out of the way. Swallow your pride. Say, sorry, kid, I can't help you with that problem. Because as soon as you start trying to defend your ignorance, you're becoming part of the problem and you're turning the kid against the school. And the kid's just trying to get by. So, dick move on your part, parents. Don't do that. If you can't help your kid with the homework, don't help your kid with the homework. Say, man, you're just going to have to struggle through this one. Let me get you a juice box. Actually, don't do that. Get him a glass of water. I'll get you some water. I'll support you in some other way. Google it, seriously. But what happens is when a parent, the kid says like, well, no, that's not what we're supposed to do. They start acting like Mr. Incredible in the movie. And everybody said, oh yeah, I can relate to that feeling. And what that is your dumbass pride getting in the way. And you're making things worse. You're making things worse because your pride is hurt because you don't remember how to do this. And I'm sorry, this ain't about you.
And I am trying to teach it the way that you learned it. I'm trying to teach it the way that you were taught, but I'm not going to teach it the way you remember, because you are programmed. You remember your programming. You don't remember understanding. How do I teach these kids? Yeah. Thanks, Cartman. So. Any questions? I like how South Park can make reference to a movie that their audience pretty much probably hasn't seen. That's like a great move. It's like when I taught high school in the early 2000s for like 3 years. And so because of the timing and because of the location of the high school, most of the quotes were Dave Matthews Band quotes, including my favorite one, where they're like, "I'll eat, drink, and be merry, for tomorrow we die." And they attribute that to Dave Matthews. I thought, all right, that's pretty much how things go. I mean, I don't blame them for that. If you want to teach your kids Shakespeare, you're actually going to have to come up with some reasons for doing that. To like look at the volume of literature that humanity is putting out right now in the last, during their lifetime even, and reach for something that's hundreds of years old. And then just read it and talk about what happened, instead of looking at the old writing and using it to understand the way people were in that location. You know what I mean? So anyway. But anyway, hopefully this has been a little bit helpful, reinforcing how division works, because it is one technique that you'll have to use when integrating rational functions. Not that in your job in the future, you're going to have to integrate rational functions by doing these techniques. If you're about to do integration by hand, you're about to get fired. That's not how things are done anymore. And I know you're saying, "Oh, well, you should teach us how things are done." And Michael, that's not my job to train you for the company. The company that you're going to be working for, they have money. They should be paying you. If you're at a company and the company says, to advance, you're going to need your master's degree, your first question should be, great, are you going to pay for it? If the answer is no, change companies. That is a company saying they don't want you anymore. That's the time to update your resume and get out. If you're at a company and they say, to advance further, you're going to need your master's degree, here is a list of schools that we will pay for and a list of programs that you can enroll in, and we will pay you to do it. That means the company wants to keep you and they're willing to invest in you. But if they're just going to say, no, you need to go get your degree on your own, get out. That company does not value you as a human being, and they should go screw. Any questions? That might be my most important lesson of the friggin' semester. You have value as a human being. Make sure that the people that think they have power over you respect that. Anyway, that's a little bit overtime. I apologize for going a little bit overtime. That's going to do it for today. I will see y'all on tomorrow. And I think we're done with the integration techniques. It's just up to the practice now. So that's it for today. I'll see y'all on tomorrow. Thanks for playing.